This is the one of the lesson in the unit number 5. So this unit number 3 here, it is this is old syllabus. Actually this notes is written for old syllabus. So unit 5, the first lesson is dielectric properties and the second lesson is magnetic properties. Okay, first let me introduce what is a dielectric material. In a vague way, I can say dielectrics are nothing but insulators. Dielectrics are nothing but insulators. So you have seen there are three, we can divide the solids into three categories on the basis of electrical conductivity. One is conductors, another one is semiconductors, and another one is insulators. Okay. So conductors which can conductors which consists of a large number of electrons inside it, free electrons. Okay. So the if you create a potential difference between the two ends of a conductor, the electrons will flow from high potential end to low potential end, so that we will get some current, electrical conductivity. For example, copper, iron, cobalt, all these are some examples of what conductors. Another one is semiconductors. So it consists of at room temperatures, at normal room temperatures. If we dope with either N-type or P-type impurities, we have additional number of charge carriers like electrons in N-type semiconductors, holes in P-type semiconductors. So if we create a potential difference between the two ends of a semiconductor, it also create electrical conductivity or some current will flow. Then what is a insulator? So insulator which doesn't have free electrons, which means each atom, if you take an individual atom of a insulator, all the electrons are complete their covalent bonds. That means all the electrons are very busy in their covalent bonds, not covalent bonds, in their bonds. So not in the sense of bonds. So they are having these insulator atom having completely filled shells. So there is a no provision for the extra free electrons. Sir, then why it is? It is not useful for electrical conductivity. It is not useful for flow of current. Then what is the meaning of study of dielectrics? Yes, even though the insulators are not so useful for the flow of flow of electrons, or is there maximum there is no, in normal conditions there is no flow of electrons, but it is useful in some other ways. For example, in intermediate you have seen, if two plates of a capacitor are separated by certain distance d, then its capacity is c. Then if a dielectric material is introduced, if a dielectric material is like mica or glass or ceramics, okay, so even dry air is also a good example of a dielectric material. Here I am interchanging the word called as insulator with what? Dielectric. Nothing, in a vague way we can call insulator as a dielectric, not exactly. Okay, for assumption, for a 2 minutes period, I am interchanging the two words, dielectrics, insulators, with each other. Okay, if we insert those type of dielectrics, what happens? Its capacity will rises. Its capacity will rises. So epsilon r is equal to epsilon. We have a definition. Epsilon r is equal to epsilon by epsilon naught. So that is dielectric constant. So that means its capacity. That later we will see. Epsilon r is equal to c by c naught. So from that c is equal to epsilon r into c naught. So which means the capacity is raised by epsilon r times by introducing a dielectric slab between the two plates of a capacitor. This is a known introduction for you in intermediate, right? Now we will see exactly what is a dielectrics. So dielectrics are non-metallic materials. Non-metallic materials means I can say metallic. What is metallic? For example, which allows the flow of electrons is called as metallic. What is non-metallic? Non-metallic means which doesn't allow the flow of electrons. So dielectrics are non-metallic materials of high specific resistance, rho. Rho. You know specific resistance rho in a intermediate Ohm's law. Okay. So and negative temperature coefficient of resistance. Negative temperature coefficient of resistance means what? For example, in conductors, what happens is as temperature increases, its conductivity get decreases. But in case of this dielectrics, as temperature increases, slowly its conductivity minutely increases. So this is called as a negative temperature coefficient of resistance minus alpha. Minus alpha means negative. Temperature coefficient of resistance is represented with alpha. And large insulation resistance. Large insulation resistance means, for example, plastic, you take wood, or you take some rubber. So they offer large insulation resistance. This is the full-fledged definition of dielectrics. Dielectrics are non-metallic materials. They are first of all not metals, okay, of high specific resistance. So they are having or higher value of specific resistance. Specific resistance means what? R into L divided by A, resistance of unit length per unit area. Okay, resistance, some other way it representation is specific resistance. Okay, R into L by A, and having negative temperature coefficient of resistance. So as temperature increases, slowly the dielectrics or insulators, these materials conductivity minutely increases, and large insulation resistance. They offer high amount of resistance. Yes, you may have one doubt now. Sir, all the dielectrics should be called as insulators, or all the insulators should be called as dielectrics? No, all the dielectrics are insulators, but not all the insulators are dielectrics. So there is a peculiar condition to become a dielectric into a insulator into a dielectric, but all the dielectrics are insulators. For example, you say rubber. Rubber is an insulator, but it is not a dielectric material. Yes, it's not a dielectric material. So which means the dielectrics have peculiar property. What is that property? Is polarization. Dielectrics will show a peculiar property. What is that? Polarization. Either it may be an electronic polarization, or it may be ionic polarization, or it may be orientation polarization, or it may be a space charge polarization. That we will introduce later in our class. Okay, so dielectrics have one peculiar property. What is that property? Polarization. What is polarization? That we will see later. Whereas insulator does not show that property. For example, if you take that one, rubber, you say that's an insulator. It's not a dielectric. Okay. So here what I am concluding that so all the dielectrics are insulators, but all the insulators are not dielectrics. Sir, what is the if and else condition? If any insulator shows the property of polarization, then that insulator is called as a dielectric material. So this is the basic introduction of a dielectrics material. So now let me introduce very important concept in the dielectrics. What is that? Electric dipole. We will understand entire dielectrics with some basic definitions. Without understanding of these definitions, you cannot understand the further topics. Okay, mostly it is a derivation topic. Okay, so that's why most of the students will ask, I think. Okay, so let me complete it. So electric dipole. So two equal and opposite charges. For example, here you take a plus q, here you take a minus q. So here plus q minus q, negative charges. That means the sign is different. So here it is a plus q charge, here it is a minus q charge. The magnitude is same. The magnitude of the charge is the same. That is q. So magnitude of the charges are same, but one is positive charge, another one is a negative charge. Is separated by a very small distance dl. Here this charge q plus q and this charge minus q are separated by a very small distance dl. This arrangement is called as electric dipole. So this is the pure definition. Two equal and opposite charges. So plus q minus q. In magnitude, two equal and opposite charges are small in magnitude. So this q value is also very small and separated by a small distance. So here plus q and minus q are separated by very small distance. This constitutes electric dipole. Okay, so please be very cautious regarding these definitions. This play very important role. So I already told you dielectrics will show some property which is called as polarization. Polarization is nothing but the formation of these electric dipoles. Simply, formation of these electric dipoles. Okay. So, for example, by certain conditions, if you apply the electric field on a dielectric material, it will form a electric dipole. That means a positive charge and a negative charge got separated by a small distance dl. So this electric behavior of showing electric dipole, formation of a electric dipole is called as what? Polarization. This is the peculiar property of dielectrics. If any insulator shows this property of formation of a electric dipole, then that insulator is called as what? Dielectric material. If this doesn't shown by any insulator, then that is simply regarded as an insulator. That's it. Next, electric dipole have peculiar property. What is that peculiar property? Electric dipole moment. Electric dipole have a peculiar property. What is that called as? Electric dipole moment. So let me complete it. Okay. So electric dipole moment. What is the fundamental property of the electric dipole is this one, dipole moment, right? So what is dipole moment? It is the product of the magnitude of the any one of the charge. So here two dipoles are in a dipole, two charges are there, plus q, minus q. Okay, q is the this plus q is the positive charge, minus q is the negative charge. Take any one of the charge because they are two equal and opposite charges. Magnitude wise they are same. Take any of the magnitude of the electric dipole, either plus q or minus q. Only magnitude you take. So by taking magnitude, anything is q only. So q, this is q. So it is the, what is the dipole moment? Dipole moment is the fundamental property of a electric dipole. Okay, so it is the product of the magnitude of the charge into distance of separation between the two charges. Distance of separation. Here plus q and minus q. These two charges are separated by a distance dl. So this q into dl, the product of q and dl is called as what? Dipole moment. I am saying once again, these definitions are very, very important to understand the concepts. So this is the dipole moment. It is represented with mu and it's a vector quantity. This dipole moment is a vector quantity. What is a vector? Which is having some magnitude and some direction. So what is the magnitude of? Obviously q into dl, the product of q, charge into dl, distance between the two charges, is called as what? Dipole moment, and it is its magnitude. Suppose q is 5 coulombs, dl is 0.01 mm. Okay, if you multiply these two, you would get what? Mu. Dipole moment, the magnitude. But the direction, what is the direction? The direction of the dipole moment is always existed from a negative charge to positive charge. So the direction of the dipole moment is existing from negative charge to positive charge. So these are the two important definitions. Once again, I am revising these two only. So what is electric dipole? If two charges, two equal and opposite charges, one is plus q, other one is minus q, are separated by a very small distance, then this arrangement is called as electric dipole. Okay. Then next definition is dipole moment. This electric dipole having one fundamental property which is called as a dipole moment. What is dipole moment? It is the product of magnitude of any one of the charge in a dipole. Okay, so q into dl, distance of separation between the two charges. So q into dl is called as a dipole moment, and it's a vector quantity. The direction of the vector dipole moment is from negative charge to positive charge. Okay, so the next important definition is a dielectric constant. Dielectric constant is represented with epsilon. It's a Greek letter, once again Greek letter epsilon, epsilon suffix r. Dielectric constant is represented with epsilon suffix r, dielectric constant. Okay, so epsilon r is equal to epsilon by epsilon naught. So the dielectric constant is defined as the ratio of permittivity of medium to the, epsilon is the permittivity of medium. Here epsilon naught is the permittivity of the free space. So the ratio between the epsilon to epsilon naught is called as epsilon r, which is also called as a dielectric constant, or also called as a relative permittivity. This is also called as what? Epsilon r also is also called as a relative permittivity. So once again I'm telling you, once again I'm telling you the definition. What is the epsilon r? Relative permittivity or dielectric constant is defined as the permittivity of medium epsilon to the permittivity of a free space epsilon naught. Okay, so there is no units for dielectric constant because epsilon naught both are having same quantities. Okay, it is the ratio of epsilons, so that's why there is no units for the dielectric constant. Okay, so the next one is electric polarization. Yeah, it is very important concept. I already told you what is a dielectric. Apart from, so all the insulators are not dielectrics, but all the dielectrics are insulators. So why all the dielectrics are insulators? They will show one peculiar property. What is that property? They will show polarization. If any dielectric atom, for example, if a glass atom, if it is polarized, then that is called as a dielectric material. Okay, that insulator, you know, glass as an insulator. If the glass atom show polarization property, then that glass atom is called as what? Dielectric material. Okay, for example, I will show you here. Okay, what is electric polarization? Here I have one slide. Let me go through. Right. So this is the general representation of a atom. What atom consists of? Nucleus, the central part. This is central part plus part. Small circle plus is called as what? Nucleus. What it consists of? Protons, which are positively charged particles, and neutrons. Okay. Around the nucleus, what we have? Electrons. So all these minus symbols are what? Electrons. So electrons revolves around the nucleus, and this big circle is representing what? Atom. So this red big signal is atom, and this small circle is nucleus. So if you clearly observe, in between nucleus and this red circle boundary, negative charges are there. Electrons revolves around the nucleus. So classically we can represent the atom like this. Okay, so this is the atom without application of any electric field. Without application of any electric field. Now what I am going to do is, I am applying some electric field in right x-axis direction. Here in this direction, here in this direction, sorry, negative x-axis direction. Here in negative x-axis direction, and from this direction, in this direction. Once again, you see, in this direction, minus x-axis direction. Okay, in this direction, here I am applying electric field. Here I am applying electric field. Okay, so then how this atom will respond? How this atom this respond? You know, positive nucleus. This nucleus will displace in the direction of electric field. You see, this nucleus will get a displace in the direction of electric field. So what is the direction of electric field? It is in the negative x-axis direction. I am applied a electric field, external electric field, in negative x-axis direction. So in this direction. Now this positive charge will get a displace in the direction of uh, negative x-axis direction. Similarly, these electric charges, these negative charges will get displaced in opposite direction, which means they move quite opposite direction to positive charge. Now what happens, you know, center of positive charge, center of negative charge got displaced from each other. You see here, you see here, you see here. You can clearly understand. Yes, here you see. This is a atom. This is a atom. Here this is the nucleus. This is the nucleus, and these are the electron clouds. These dots are what? Electron clouds. What here am I applying? Here I am applying the electric field. So in the direction, arrowhead represent what? Direction of electric field. E is what? Electric field. So in the direction of electric field, what will move? Nucleus. Nucleus will got displaced in the direction of electric field, like this. Here nucleus will got displaced in the direction of electric field. Now, if you clearly observe, these more number of electrons, more dots, black dots you see. So most of the black dots got displaced in a direction opposite to electric field. Okay, this electric field pushes this nucleus in the direction of electric field, and the same electrons got displaced in a direction opposite to electric field. Got a direction opposite to electric field. Now what happens? All these negative charges have center of negative charge. You know concept of center of mass. Center of mass in intermediate. What is center of mass? For example, if you take the object, at one particular point, this object got balanced. This particular point is called as what? Center of mass. This particular point is called as what? Center of mass. Similarly, there is a center of positive charge and center of negative charge. So here nucleus have positive charge. So center of positive charge is at center for a atom, and center of negative charge normally for a, here you see in this diagram. In this diagram, center of positive charge is at center. Here you see the distribution of electrons. Here all the electrons approximately uniformly distributed throughout the atom. Okay, even though electrons negative charges distributed throughout the atom, the entire negative charge got balanced at a particular point, that is at center. So that is center of negative charge, like the same concept of center of mass. Even though at everywhere of the mass of the cell phone, it is having throughout its length, it is having some mass, but at a particular point, this cell phone gets balanced. Okay, so are you able to see? So this point is called as center of mass. Like that, even though these negative charges are distributed throughout the volume of the atom, the entire negative charge is appeared to concentrate at a particular center point. This point is called as center of negative charge. Here, center of positive charge, center of negative charge coincide with this coincide with each other, coincide with each other. Here, plus at the same place, minus is there. That means the center of negative charge, center of positive charge coincide. Okay, there is no polarization. Now in this case, in the second case, B case, what happens? Center of positive charge displaced from center of positive charge displaced from here to here. Similarly, center of negative charge displaced from here to here. Now what happens? A red circle plus is there here, a red circle minus here. Okay, so a positive charge, a negative charge separated by certain distance. This is called as a electric dipole, formation of a electric dipole. This process is called as polarization. You clearly observe here. Yes, here this dot is center of positive charge. This dot is center of negative charge. Here you see this dot. Small dots are electrons, but there are two big dots. This is a plus big dot. This is a another big dot. What is this big dot? This big dot is plus Zt. Plus Zt means nucleus. This big dot is what? Center of negative charge. Here, due to the application of electric field, center of positive charge got separated from center of negative charge, and the electric dipole is formed. This procedure is called as polarization in dielectrics. This is called as what? Polarization in dielectrics. This is very important. Once again, what is electric dipole? That's why this definition is important. So center of positive charge got separated from center of negative charge. So there is a distance between a positive charge and negative charge and form a electric dipole. This process is called as polarization in dielectrics. So here you see. This process of producing electric dipoles which are oriented along the electric field direction is called as polarization in dielectrics. So normally center of positive charge, center of negative charge. So this is center of positive charge, this is center of negative charge. These two coincide with each other. But due to the application of electric field, so center of positive charge and center of negative charge got separated. And so this is a one center of positive charge here, here negative charge. So there is certain distance between these two charges. So electric dipole is formed. This process of producing electric dipole, here you see. So due to the application of electric field. Okay, so here I apply electric field in what direction? Negative x-axis. Okay, which means in this direction. Which direction? In this direction. In the same direction, plus charge will move. In opposite direction, minus charge will move. Finally, it produces electric dipole. So the process of formation of the electric dipole due to the application of external electric field is called as what? Polarization in dielectrics. If any insulator is show this property, that insulating material is called as a dielectric. That's it. This is the polarization in dielectrics. This is the polarization in the dielectrics. That's it. As simple as that. I already told you all the dielectrics are insulators, but not all the insulators are dielectrics. Sir, what is the necessary and sufficient condition? If any insulator shows the property of polarization, then that insulator is called as a dielectric. So this is the polarization. The process of producing electric dipoles which are oriented along the applied electric field direction is called as polarization in dielectrics. So the next definition is polarizability. So this is also very important definition, because already you have seen in dielectrics that the important questions in the dielectrics is what is electronic polarization and derive an expression for electronic polarizability. Next important definition is what is ionic polarization and derive an expression for ionic polarizability. What is orientation polarization and derive an expression for orientation polarizability. Okay, so this polarizability is very important definition. So in a simple language, what is polarizability? Polarizability says the magnitude of polarization. So magnitude of polarization. For example, you and your friend are invited to eat some sweets. Okay, so your eating capability is 2 sweets, your friend eating capability is 4 sweets. So eating capability is more for your friend rather than you. That eating ability is represented here is polarizability alpha. That is eating ability. This is polarizing ability. So if I take two atoms, if I apply electric field on the two atoms, they will get polarized, which means formation of electric dipoles. Okay, so the magnitude of electric dipole moment is more for which atom? That is more polarized. So that is called as polarizability. Yes. Here, let me explain. That is the general. This is the purpose to understand what is polarizability. So when the strength of the electric field E is increased, then the strength of the induced dipole moment is also increased, which means that, for example, here use in this definition, in this example, yes, yeah, in the same example, right? So here you take the applied electric field. So this arrow length represents the magnitude of applied electric field. For example, if I increases the length of the arrow from here to here, okay. Suppose if the length of the applied electric field till this particular line, such a long line it is. Okay, so what happens if I apply this long electric field, which means if I apply a electric field with more strength? So long electric field represents what? Strength of the electric field. If I apply a electric field with more strength, what happens? You know, this dot will displaces to this point, which means this dot plus nucleus will displace more in the direction of applied electric field. This center of negative charge will displace much more towards the right side. So this negative center of negative charge, this dot center of negative charge will much displace towards the right side, and this center of positive charge much displace towards the minus x-axis, which means it will displace more towards negative x-axis, towards left side. This plus ZD goes to left side, more left side. This minus ZD goes to more right side, which means the distance between the charges increases in a clear manner. What happens? Let us go to the dipole. Okay. Yes. If I apply here, yes. Okay. Here I apply strong electric field. Strong electric field. Now what happens? You know, this plus q goes to here. This minus q2 goes to here. Then what happens? Nothing happens. Still it is electric dipole, but its dipole moment got increased. You see, what is the formula for electric dipole moment? Mu is equal to q. Yes, in this case, yes, let us assume here is a plus q, here is minus q. The magnitude of charge is the same, q only, but the distance got increased. Now plus q and minus q separated by this much distance, more distance, due to the application of more electric field. Okay, so as dl increases, as this dl distance between the two charges increases, q into dl also increases. As q into dl increases, mu also increases, which means that electric dipole moment value increases. This is the mean. Here you see, mu electric dipole moment is directly proportional to what? Applied electric field. If you remove this proportionality constant, what you are able to get? A constant alpha. If this is proportionality, mu proportional to E. Mu means dipole moment is directly proportional to applied electric field. So one moment, right? This mu dipole moment is directly proportional to applied electric field. If you remove this proportionality constant, you would get a equals. If you remove proportional, you would get a constant that is equal to alpha. What is alpha? So this, you see, this is alpha, this is proportional. It looks like same, but they are different meanings. This is proportional, this is alpha. Here alpha is a proportionality constant. This alpha is called as polarizability. This alpha is called as what? Polarizability. So from this definition, mu is equal to alpha into E. From this, alpha is equal to mu by E. So what is mu? Electric dipole moment per unit electric field is called as what? Alpha. So it can be defined as induced dipole moment. So mu is called as what? Dipole moment per unit electric field is called as what? Alpha. Simply, polarizability says that if you apply a unit electric field, what the amount of dipole moment got produced. The ratio between the two is called as what? Polarizability alpha. Next important questions are this: calculation of electronic polarizability, calculation of ionic polarizability, orientation polarizability. Okay, so in that, polarizability concept is very important. The definition you remember: mu by E is called as what? Polarizability. So mu is a dipole moment, E is a applied electric field or unit electric field. The dipole moment mu by electric field is called as polarizability alpha. Next, polarization vector. Mu by E is called as polarizability, whereas mu by V is called as dipole polarization vector. Here, mu dipole moment per unit volume. Dipole moment per unit volume is called as polarization vector. This is the definition of polarization vector. Okay, so you just go to the previous concept. What it shows that you just compare these two. Mu by E is called as polarizability. Mu by V is called as what? Polarization vector. This is the difference between these two. The dipole moment per unit volume, mu is called as a dipole moment, divided by V is called as what? Volume. So the dipole moment per unit volume of the dielectric material is called as a polarization vector P bar. This polarization vector also represented with P bar is equal to N into mu bar, where N is the number of atoms in a dielectric material. For example, you take this much dielectric, this is a dielectric material. It is made up of with how many number of atoms? Capital N number of atoms. Each atom having a dipole moment mu. So that number of atoms n into dipole moment to each dipole moment of average individual dipole moment atom. So n into mu bar is also called as what? P bar. Another definition. This is another sort of definition. What it is? So polarization vector is also defined as a number of dielectric atoms in the unit volume into mu bar, average dipole moment of that each atom in that unit volume is also called as polarization vector. But you just remember one definition. So P bar as mu by V, dipole moment per unit volume. So this definition will useful in next derivations. P bar polarization vector can also represent as n into mu bar. Okay. Right. So the next definition is electric displacement vector. Electric displacement vector or electric flux density or electric induction. This is very similar to magnetic flux density or magnetic induction or magnetic uh, flux density. You see what is the definition of the magnetic flux density. Right. So let me see this, right? So anyhow, I'm saying that I'm going to explain this definition. D is equal to epsilon into E. We can say that the electric displacement vector D is the product of epsilon into E. So what is epsilon? Permittivity of the medium of the dielectric. Permittivity of the medium of the given dielectric, and E, applied electric field. So the product of the field strength, applied electric field strength, E bar is the applied electric field strength. Okay. So the product of E bar and epsilon is called as D bar. This is the simplest definition. D bar is equal to epsilon into E. So we can define D bar electric displacement vector as product of epsilon and E. So what is epsilon? Permittivity of the medium of a dielectric material into E bar, the applied electric field strength, E bar. Okay, this is the definition of electric displacement vector. And already we know we can write epsilon as epsilon naught into epsilon r. How we can write? How we can write? You just go back. You go back. You have one definition. Electric uh, epsilon r. Yes. Epsilon or dielectric constant or relative permittivity, epsilon r can be defined as epsilon into epsilon naught. So from this, what is the value of epsilon? From this definition, what is the value of epsilon? Epsilon is equal to epsilon r into epsilon naught. Just to substitute that value here. Just to substitute that value here. So epsilon is equal to epsilon naught into epsilon r. This is the another way of representation of D bar, electric displacement vector. Now let us see the relation between P bar and E bar. So we know already in dielectrics, yes, it is not in our syllabus, but we can write D bar as epsilon naught E plus P. This is from in intermediate you have dielectrics. When a dielectric slab is introduced between two plates of a capacitor, its capacitance got increased. So if the further extension will gives the this particular relation. Okay, so it's none of our business. We will use that definition. D is equal to epsilon naught E plus P. We are using that relation. Okay, but here our important point is in this relation we can substitute D as epsilon naught into epsilon r into E. Previously we got D as what? Epsilon naught into epsilon r into E. So this D bar can be written as what? Epsilon naught into epsilon r into E. So epsilon naught epsilon r into E. This is replaced with what? D. So D is equal to yeah, D is equal to epsilon naught into epsilon r into E is equal to epsilon naught E plus P. So from this definition, if you realter this equation, okay, P bar is equal to what we get? Epsilon naught into epsilon r minus epsilon naught into E. So from the above equation, if you rearranging this equation, we would get P bar is equal to epsilon naught epsilon r E minus epsilon naught E. If you take epsilon naught E as common, what is the leftover factor? Epsilon r minus 1. This is the relation between P bar and E bar. This is useful in next derivations. Okay. The next definition is electric susceptibility. What is electric susceptibility? P bar is directly proportional to E bar. So what is P bar? P bar is polarization vector, is directly proportional to applied electric field. Sir, previously you said that mu is directly proportional to E bar. Yes. If you go back to polarizability, yes, here I stated that mu is directly proportional to E. What happens if I apply strong electric field? If I apply strong electric field, the distance between two charges increases. If I apply this much electric field, so let us assume this is the distance between a positive charge and a negative charge. If I apply this much, if I apply, if I apply this much electric field, this is the distance between two charges, plus charge, minus charge. This is plus field, this is minus field. Now, if I apply this much electric field, now the distance between plus charge and minus charge increases. Okay, so as plus charge, minus charge got separated by more distance, what happens? Q into mu increases. What is mu? Mu is equal to Q into dl. The distance between, so yes, Q does not changes. This is plus Q. As I apply more electric field, so the distance increases between these two charges. This is plus Q, this is minus Q. Okay, right. So plus Q minus Q got the distance between two charges increases. Yes, nothing happened to the magnitude of charge, but the distance got increases. That means dl value increases. Dl into magnitude of charge Q. So Q into dl is called as what? Mu. So mu increases by increasing the applied electric field. As I apply more electric field, more dipole moment will be produced. This dipole moment per unit electric field is called as what? Alpha. In the same manner, this dipole movement per unit volume is called as what? Polarization vector, which means that as this mu value increases, as applied electric field increases, as I goes from this much electric field, less small electric field to big electric field. Now the distance between the two charges increases, which means mu value increases. As mu value increases, P value also increases. How mu value increases? By increasing the electric field. So as electric field increases, mu increases. As mu increases, P value also increases for a constant volume. This V value is constant, let us say. So E proportional to mu, mu proportional to P. So P proportional to E. Okay, so the same thing here I written. Polarization vector is directly proportional to applied electric field. So polarization vector, if you take out the proportionality constant, what you would get? A constant. So if you take out the proportionality, you would get a constant. The proportionality constant here is epsilon naught into chi e, where this chi e is called as what? A susceptibility, electric susceptibility. So chi e is equal to P bar by epsilon naught into E. So if you rearranging this equation, rearranging this equation number 1, so what you would get? Chi E is equal to P bar by epsilon naught into E bar. Okay, so this is the we can say, what is the definition? Polarization, electric susceptibility, in a definition we can define it as it is the ratio between the polarization vector P bar to the epsilon naught times the applied electric field. So P bar polarization vector divided by epsilon naught times, which means permittivity of the free space, into E applied electric field. The ratio between P bar to epsilon naught into E is called as what? Electric susceptibility. Electric susceptibility is the ratio of polarization vector to the epsilon naught times the applied electric field. This is the definition of electric susceptibility. So the relation between chi, here you see already we have this relation P bar as epsilon naught into E epsilon r minus 1. Sir, from where you got it? Here, from here, just I derived the definition. P bar is equal to epsilon naught E into epsilon r minus 1. So just substitute this value here. P bar in the numerator, substitute this value. Yes. P bar is equal to epsilon naught E into epsilon r minus 1. Denominator is epsilon naught E. So epsilon naught E cancels out. So susceptibility chi E is equal to epsilon r minus 1. This is the relation between epsilon r and susceptibility. So with this introduction part